coming out today. We really hope you're going to learn a little bit about science and about science careers. In a few years, you guys are going to be out there looking for jobs and thinking about careers. You're going to learn about some of the careers of the gentlemen and ladies who are here today to present and tell you a little bit about their work. This is possible because we had some very good supportive industries in Kentucky which helped pay your meeting expenses and your lunch today. We've also have some graduate students who were able to join us today as the result of the contributions from our industries. Ashland Oil Foundation, Super America, United Catalyst Incorporated, Martin Marietta, Ashland Petroleum, and we even had some individuals who helped us out a little bit. So we very much appreciate their support, and we hope that you will remember who those industry sponsors were. Our first speaker is Jeff West, and Jeff is from the East Kentucky Power Corporation. He's here today to talk to us about biological research in the electric utility industry, to search for an answer to the electromagnetic field dilemma. You're going to learn a little bit about magnetic fields. I would like for each speaker to take a few minutes to tell you a little bit about themselves, where they're from, a little bit about their jobs, and if you're interested in their job, what kind of education would you need? What would you need? What would their advice be to you? So, Jeff, we'll let you start.
Thank you. Good morning.
Good morning.
Great. Talk about my career. I guess you can tell by looking at me. Mine's been rather short. I'm not that old. But I have been in the workforce for about 4.5 to 5 years now. I went to school at Murray State University and got a degree in engineering and physics. I'm originally from around the area. I went to school at Henderson County High School, and because of UK's football team this year, I had to go back to my high school to get my entertainment. They're doing really well this year, but UK is kind of terrible. As far as my first job when I got out of school, I went to Huntsville, Alabama, and worked for Teledyne Brown Engineering, which they are a defense contractor, and they do multiple areas of defense. But at the time, I worked for the Strategic Defense Initiative, which my main job at the time was working on optical arrays for missiles in the Star Wars, the Ronnie Reagan Star Wars. It was a really interesting field, but there's a lot of people down there. There's a lot of PhDs, and it's a real thinking area, but it's also very interesting. At the same time, when I first was interviewing for that job, I also interviewed for Martin Marietta here in Paducah and was offered a job here, but at the time it was a choice of that, not really the one place or the other. It was more of a choice of where I wanted to live, and I wanted to go south at the time. If you are interested in working for Martin Marietta or any of the businesses in Huntsville, Alabama, the degree at Murray State University Engineering Physics is a really good degree. That's how I got my track, inside track to go to Huntsville, was that they heavily recruit that degree at Murray State, and at the fairs, the college fairs they have there, that's where I met a recruiter. And so that's a really good degree. If you're looking at getting an engineering degree, you might want to look at UK or Louisville, because one thing I learned at the time and I had to make a choice on was whether I wanted to be a professional engineer, accredited professional engineer, and you have to go to an accredited school to get that. Murray State at the moment does not have an accredited engineering program. So my background is kind of both in physics and engineering. What I want to talk to you about a little bit today, back up a second. I now, of course, work for East Kentucky Power, and I have worked there for 3.5 years. From the time I first got there, I got into the field of electromagnetic fields. I work in the research and development department at East Kentucky Power, and that's kind of unique. Not many electric utilities have their own research and development department. I'm very, very honored and happy to be in that area because it gives me a lot of leeway to do a lot of different things. I don't do finance on every day, and I don't do legal every day or something like that. I get to do a little bit of everything. So I'm constantly going back to the books and having to find out something new. And with EMF and the biology part of it that we got into, seeing as I don't have a biology degree, I had to go back and learn a little bit. With electromagnetic fields, I like to get a background from everybody I'm talking to kind of understand where you are in your understanding of this. How many people here have heard of or read about the issue of electromagnetic fields and how it might cause possible health effects. Has anybody heard about that? Well, it's good to know statistics do work sometimes. Because the surveys that have been shown say that about 65%, 70% of the people in the U.S. have heard about the issue at one time or another. And the second question I'd like to ask is how many people here feel they have a good understanding of the science behind the issue? Drop off. And that's where a lot of the problem lies in the public perception, is the lack of understanding. And that's what I'm going to try to help with today. After reading about that, how many of you are concerned about that as affecting your life? All right. If you're not concerned, this was a title of a paper that came out last year in Legal Times. Will power lines be the asbestos of the 1990s? If I were to tell you right now that electromagnetic fields were as dangerous as asbestos, would you be concerned? Oh, nod our heads. Okay. Fortunately, that's not the case right now, but it's a big question, and there's a lot of research going on to try to solve that question, to answer that question. Hopefully, it'll never come to this, because at this point, this is not where we're at right now. But this came from a legal paper, and lawyers, like to look for blood, so this is a good title for them. Now, try to explain magnetic fields a little bit. Let me ask you another question. How many of you here in your physics classes or your science classes have studied magnetic fields to some degree? A couple of you understand what they are. When I work with things, I have to have an understanding in my head, a model in my head, a picture of what's going on. I can't just deal with the invisible. And so you have to make magnetic fields real to people. And what this is a slide that's in a lot of high school and college textbooks of a little simple experiment. What you're seeing there is a picture of a bar magnet, a simple little rectangular bar magnet. You lay it down, you put a piece of plastic glass over the top of it, or just a thin piece of glass. And you take small iron filings and you just throw them down the glass. Now, if you just throw them down in a random pattern, they should look random, but they are affected by the magnetic field from that bar magnet. And as you can tell in the vicinity right around the bar magnet, that they're aligning themselves in a pattern. And that's the magnetic field. And that, for me, is a picture that I have to use. There's a graphical representation of that. You draw field lines just to see the force that's associated with the field lines. The Earth is represented by a huge bar magnet. The Earth has its own magnetic field associated with it. That's why your compass points north. We'll move along quickly. When we get into the power industry, you're not talking about, the first two slides have to do with what's called a static magnetic field. Those fields do not change from day to day very much at all. And they're pretty much constant. They don't move. They stay in that orientation consistently. When you deal with the utility industry, we have 60 hertz alternating current power. And that is a different type of field that's generated. The reason it's different is because it changes 60 times a cycle at 60 hertz power. And it actually changes direction twice in that cycle, so it's 120 times a cycle or second that it changes. Another little experiment you can do if you hook up to a battery, and again, this is going to be a static magnetic field. It gives you another feel for things. If you hook up a wire to a battery, and you don't want to do this because it's not real safe, but if you could, and lay some compasses around that wire, and you have current going through the wire, then the compasses are all going to line up in a direction that points in a circle around that wire. So currents do create magnetic fields. That's the point I'm trying to get across. With AC power, if I were to animate that little drawing, the current would change directions 120 times a second, and the little compasses would be rotating like this. And the theory is that some people have is that that's doing that to the cells in your body. Now, physicists, and me being a physicist, say that that's not possible because the fields generated within your own body are stronger than the fields that you're going to be in typically in day-to-day life. So there's just really, your body should see no effect from these fields. But biologists say that there is ways that can affect your body. Several years ago, they were looking at the issue of electric fields. Remember, power has two components, it's electric and a magnetic field. And several years ago, they were looking at electric fields as being a possible health concern. That's kind of died off. Nobody could find any proof to lead into that. And so they went into magnetic fields. And it proved that the two are different. What the top drawing on the left there shows is a light plugged into an outlet, but not turned on. In that instance, there is an electric field. Electric fields are created by potential. There you got the potential to do work. Electricity sitting there. It's just not doing any work yet. So you have an electric field, but you do not have a magnetic field until that appliance is turned on. At that time, you have down here in the little drawing on the bottom, you have both an electric and a magnetic field. And that's where the concern comes in, is the current flowing through the wire, and you get too close to it. And people are concerned that that's the problem. Lovely graphs, or pictures. Just sit back and look at it for a second. What this is a drawing of the frequency spectrum of light and all the electromagnetic fields that we are involved with. Up here at the top you have ionizing energy, above visible light, and from visible light down they classify that as non-ionizing energy. Ionizing energy, everybody knows ultraviolet X-rays and gamma rays are bad for us. That's why when you get X-rays you have to be shielded and so forth, because they can actually ionize the cells in the body. But below that there is not enough energy to actually ionize. Now we know that infrared and microwaves, and this area radar even, can cause you the cells in your body to heat up. And that again is not very good for you. But as we go down the frequency and we get further down, we're getting down to AM radio and video display terminals. And transmission lines are down here at 60 hertz. You know, we're looking at 10 to the 12 hertz up here for radiant heating, visible lights above 10 to the 14 hertz. So the amount of energy that's in the electromagnetic field put off by transmission line is not that great. So, you know, that raises a question by the physicists of how is it possible that these could affect us? And again, for the pictures in my head to help understand things, the wavelength of a microwave, the field from a microwave, is only 12 inches wide. Sorry, 12 inches wide, 12 inches long. Television is 1 to 18 feet. But the wavelength for 60 hertz power frequency fields is 3,100 miles. That's for one wavelength. It takes 3,100 miles for it to get through. Now, the way we measure magnetic fields is in a unit called milligauss. And again, milligauss to me is just purely arbitrary. I mean, even if you gave me the definition, I could understand it. Like if I told you a second was the amount of oscillations it takes a cesium-1 whatever atom to oscillate so many times, you wouldn't understand what a second was until I gave you a watch and said that's a second. So the way we explain magnetic fields to people is we actually give them a meter, which we have a meter in our office, actually 3 of them, that you just hold it in your hand and put it in the point's face, and it gives you a little readout of the magnetic field. And we take these to our consumers when they're concerned. We'll measure the different appliances in their house. And the only way to really get a feeling for these is to compare one appliance to another versus power lines and so forth. This gives you a range of the magnetic fields that you encounter in your home. A very important point that's shown on the slide here is that we have 3 different distances that the measurements were taken at. The first one's at 0.03 meters, which is just a couple inches. 0.3 meters is about a foot, and a meter is a little more than 3 yards, or a little more than a yard. You can see that as you get away from the source of the magnetic field, the fields drop rapidly. For say a microwave oven, you could have 750 to 2,000 milligauss up really close to the microwave. But if you get out to about a little over 3 feet, it's dropped from 750 down to 3 milligauss. It drops off very rapidly. And that's true with most appliances, is that if you get, say, 3, 4, 5 feet away, the fields have almost dropped off to nothing. Same way with the power line. As you get further away from the source, it's going to drop off. But it takes a little while longer with a power line for it to drop off, so you need a little greater distance. That was a compilation of a whole bunch of different appliances. That's why a range was given. Each appliance is different. Your hairdryer is not going to be the same as my hairdryer, so the fields from it aren't going to be the same. What this is right here is a more practical slide of some measurements that we took at my home and at work and so forth, and it gives you the same kind of information. Again, the microwave was the highest contributor of fields here, whereas fluorescent light, right up close to it, was about 100 milligauss. Excuse me. A normal incandescent bulb was only 4.4, up real close to it. So there, you can tell from looking at this, there's two things you can do. You can stay away from the appliances that you know give off the most magnetic fields. And that's a prudent step to take. Although there's nothing proven that it does you any help, it's not going to harm you to do it. With that same meter, we can walk around and we can actually put it on somebody and it'll record every time it makes a measure, like every 3 seconds or so forth. And we can record several days, and that's what this graph shows. Somebody actually wore this for a while, and there's a legend that's put on it. They wore it from 2:45 one day until 4:20 the next day. Right here, when it's real low, this is the magnetic field over here. It was real low when he was using a desktop computer. This large group in here is when he slept under an electric blanket. This large, huge spike right here that goes up to 450 milligauss was an electric razor. We've got a number, let's see, number 6 is some HVAC motors, microwave oven. We get back at his desktop computer. And here's where people get concerned about transmission lines and think they're the worst. This is a good comparison. This is a transmission line he walked under. And this is walking through a distribution substation. So you can see the electric razor is much higher than the transmission line. Is the electric blanket is about equivalent. Key issues being addressed. Is there a health effect? And that's usually done by statistical association. What is the cause of the effect, which I'm going to get into in just a second, is the biological plausibility. Can it happen? Is there a mechanism within our body that will allow that to happen? And the third one is, what is safe? And that one really can't be answered until one of the first two is answered. Because you can't really know what is a safe exposure if you don't know how it affects the body. You just have a rough idea that it might. So, is there a health effect? The statistical association, the way that is done, how many people have ever heard of epidemiology? Okay. Epidemiology is the study of disease in human populations. It is, some people give it the definition of science of statistics. I have a hard time calling statistics science, but they are very useful. Epidemiology is very useful in leading us in certain directions to put our research dollars. They will indicate if there's a possible cause with something, but epidemiology will never prove a cause-effect relationship. It just can't do it. We're talking about statistics, not actual hard proof. But it is a very useful tool, and there have been a lot of epidemiological studies done with electromagnetic fields to find an association. And most of the studies you read about are epidemiological in nature. If you'll see an article that comes out and says, study finds that there's a three times greater risk for you to get a certain type of cancer, more than likely that was an epidemiological study that did it. The way that works is they'll go out and they'll find a group of people that say have leukemia, which is one of the concerns, childhood leukemia with electromagnetic field. They'll go out and find children with leukemia and put them on what's called a test group. And then they'll go out and find a demographically similar group of children that don't have leukemia, and they'll measure the fields so that those kids were in over a certain period of time, compare the two, and if your assumption is true, then the kids that had leukemia would be exposed to higher magnetic fields than the control group. There's a lot of difficulties in epidemiology, a lot of questions that have to be answered. If you throw a whole bunch of beans down on a table somewhere, you would expect that they would be thrown down in a random pattern, but if you actually look, you may find clustering of groups of these beans laying around. And that's the same way in a human population. You may find in a neighborhood a large number of occurrences of a particular disease and say something's causing that, but it may be random chance that's doing it. And that's when the statistics come into play of trying to determine, is it random or is something going on? Back to the biological plausibility. This is just for looks. I'm not going to discuss biology too deep. But we recently began funding some research at the University of Kentucky that they're looking at cells and the signal transduction mechanisms within that cell and the pathways to start to find a possible plausibility biologically of electromagnetic fields or magnetic fields affecting the body. What they're actually doing there is kind of interesting. They take bone-type cells or nerve cells and they'll put them in a culture dish. And then they'll scrape load them, which they had to explain that to me, but it sounded kind of archaic. They take a substance and they actually rub it across the cell, and that's supposed to put the substance into the cell. They take a little knife and just kind of rub it across, kind of like you're putting peanut butter on a sandwich or something like that. And the substance they're putting in the cells is called acorn. It's a photoprotein that's derived from jellyfish. The jellyfish will secrete into the salt water, and it glows, it bioluminesces. What they found out is that when you put that substance with calcium, that the calcium will cause the acorn to give off a photon of light. In your normal cells, you have a regulated amount of calcium within a cell and a large amount of calcium outside the cell normally in your body, and the membrane controls how much is in that cell. Well, what happens usually when a cell divides is the amount of calcium will grow within the cell before it splits. If the acorn is in the cell and it starts to give off more light, you can tell that the calcium is growing within the cell. So they're actually putting calcium in an acorn in the cell and putting a magnetic field to the culture disc and seeing if there are growth rates when they apply a magnetic field, if there's a rise in the amount of light that's given off. So it sounds kind of interesting, and right now they're kind of leading to the conclusion that they don't think that there's anything actually going on. They actually found out that what artifacts they were finding may possibly be attributed to damaging the cells and putting the acorn in them. But that's still ongoing, and we're funding that along with the Electric Power Research Institute, which is a very large organization nationwide that has over 700 members, utility organizations, and everybody puts in money for different types of research, and this just happens to be one area that we spend a lot of money on. We also have software programs at work that make our lives a lot easier. When I first started doing this, I sat down and got my book out and started doing the old hand calculations on a piece of paper, and it took me 30 minutes. That was after I got reacquainted to how to do it. It took me 30 minutes. It's a long, drawn-out calculation. Now we have software where it takes me about 5 minutes, and that's a great help. And it outputs for transmission lines. I can put in the parameters, and it'll give me a little graph that shows for that transmission line at a certain instance what are the magnetic fields. And this is how a transmission line magnetic field profile looks. Right here is where the transmission line is, and directly under it you're going to get the highest field. And you can see it falls off fairly rapidly as you get out of here at what we call the right-of-way, which is the amount of land that we own under that transmission line. We've fallen from almost 30 mellogauss down to about 7 millagauss. The way most utilities do this, they buy this land and nobody's allowed to build on that land for safety reasons. So we usually use the edge of right-of-way because there's no homes inside that right-of-way. Other things we've done as far as research, again, we participated with EPRI, where we actually took these meters out to people's homes and let them wear them for a little while and accumulated data. We put this in a large database to see what kind of field levels people were getting in their homes. This is a slide of a combination of two studies. Another study was done for workplace environments. This is a compilation of both of them. You can see that people that work in substations and work on transmission lines get quite a bit more exposure to magnetic fields than those of us that work in the office, or well, the office is pretty equivalent to a home. They're roughly the same. So that's another study we did. How does this affect the electric utility industry? How does the science of the issue, how does it come back to us and hit us at home? And this is what everybody's interested in. This is what drives everything. Last year was a fun year. This is a survey done by the Edison Electric Institute, and it's done every year in the fourth quarter for the first 4 slides, and there's about a 5% increase yearly in the number of people that heard or read about EMF. First quarter last year, there was a media barrage with the issue. There was things that came out in the paper, is my electric blanket killing me? There was news articles done on TV. It was incredible the amount of stuff that came out. And it hit a lot of people. We got a ton of phone calls and went out and started visiting a lot of consumers about the issue. The survey was done. It's normally done in the fourth quarter, but the next quarter after that, they did a survey again when the media barrage came out, and it jumped, instead of 5% per year, it jumped 12%, or excuse me, I get my numbers right, 8%. Can't add real quick. Well, it jumped a tremendous amount in a short period of time. 15, 18%, 45, 60. A lot. But the thing about it is, the media wasn't so bad, and the reason being is because you'll look in the first three quarters, first three times this was done, how much of a threat do you consider EMF? Very serious. It grew a little bit in the first 3 years, 5 to 7%, 7 to 10%, but when the media barrage came, that number dropped 5%. And the way I attribute to that is that this is an issue that people don't understand. So if somebody tells me something, they get upset about it. And I'm the same way. If I don't understand it and somebody tells me there's a problem, then I'm going to get upset about it. But once we go out and educate people to understand actually what's going on, then the level of concern drops somewhat. And that's been my experience with all the home visits I've had, is that people are really alarmed when I walk in, but once we give them the meter and let them walk around the house and see that, hey, you know, my hair dryer is giving off more magnetic fields than the distribution line or the transmission line, it really changes their opinion of the subject. So that's how I kind of attributed that. But again, you know, as electric utility, how does it affect us? The company I work for happens to generate and transmit power, so we own the generating plant and transmission lines. We don't actually own the lines that enter your home. And unfortunately, transmission lines, the large power lines that we own, are the ones that have got the worst reputation. But this slide shows the amount of transmission lines, or different power lines across the U.S. And you see the homes, the lines that serve the homes make up 98% of it. Only 2% of the lines out there are transmission lines, but they get 70% of the attention. And this is kind of what it boils down to. We've spent probably $100,000 to $200,000 in the past few years nationwide at researching this issue. And the Department of Energy has a program going on that's just supposed to have started a couple of years ago, but that's really getting started now. Well, they're going to spend $65 million over a 5-year period to do research, coordinated research. That seems like a lot of money, but it's small compared to what would happen if somebody were to come to us today and say, okay, 2 milligauss and above is bad for you. You've got to design your power lines to stay below that. Well, the Missouri Public Service Company did a study on their 1,300 miles of transmission line, which is small potatoes if you look compared to what if you look nationwide. And for them to get their lines, engineer their lines, and redesign them to get down to 2 milligauss, it was going to cost them $350 million. Now that's roughly the same or more money that has been spent in several years before in research. So you can see that this could be $1 billion undertaking if it were to happen. And it comes back down to who's going to pay for that. We're a nonprofit organization, and even the investor-owned organizations wouldn't have the money to be able to absorb that. So it would go back, it would fall back to the people that are paying the bills. It's not something that we want to jump into immediately and say, okay, let's do something about it. We've got to find out, is there justification for doing it? And the last slide. Can we read that? Kind of where are we now? Right now, the research is still going on. The majority of people out, the scientists and so forth, don't believe that there is an issue. I haven't changed my lifestyle, and I've been looking at this for 3.5 years. It's something that we do need to address, but it's not something that we need to go wholeheartedly into at the moment. If you want to put this on a risk assessment scale, I saw somebody, or heard somebody put this in perspective one time. If you're worried about magnetic fields, first of all, worry about getting in shape, worry about eating the right foods, lowering your cholesterol level, worry about getting radon in your home checked. This concern, if you were to take the data that it is now and you compare it, it's less than the risk of dying in a car accident. It's less than the risk of several other common things you can do. It's low on the list, but it's a hot issue because a lot of times it's brought up with leukemia in children, which is a sensitive issue. I have a 2.5-year-old kid, and if I were to get my kid were to get leukemia right now, I'd be fairly emotional. That's understandable. So that's why it's a delicate issue that we have to address. But it's going to be ongoing. I don't see an answer in the near future. I think with time we might get an answer, but like I said, it's going to keep me busy for a while. I'm right on time. Are there any questions? You can ask me about what I do or anything like that.
What does the data show on the difference in underground transmission and above the ground transmission? And why don't we go in that direction? It looked better if nothing else.
It's true, it does look better. The reason we don't do it, there's two reasons. First of all, we did our own study. The cost to do underground transmission at present is anywhere from 6 to 12 times more expensive than to do overhead. And with the technology that we had several years ago, to put the lines underground did not do any better as far as your exposure to magnetic fields, because there was no way to put them in there close enough to get good cancellation. You're actually taking a line that's 25, 30 feet above ground, and you're putting it about 6 feet underground. So distance, like that one slide I showed, is the most important key from exposure. The further you get away from the source, the better off you are. If I put a line 6 feet underground, I'm 6 feet away as opposed to 25 feet away, and earth and walls do nothing to block magnetic fields, unlike electric fields. Your home or any material will block an electric field. But more recently, we have gotten the technology where, like I said, when I was talking about cancellation, if I take two wires and put them together and they don't have the exact same power going through them, which the 3 wires that are up there now are out of phase somewhat, there's cancellation involved with those fields. This wire's magnetic field will cancel somewhat this wire's. The closer I get those wires, the more they cancel and the less the field is. And we now are getting the technology better that we can put these underground very close together and cancel out. But again, it's very expensive to do, very time consuming.
Any other questions? Let's thank Jeff for a very good talk.